Welcome to section 16.3. In this section, we're going to be continuing our discussion on line integrals and talking about the fundamental theorem for line integrals. So, the first thing we want to think about when we hear the term fundamental theorem is the fundamental theorem of calculus that we learned back in Calc 1 that says if you take the integral from a to b of f prime of x dx, that's equal to f of b minus f of a, right? We take the antiderivative and then evaluate between the endpoints. In the case of line integrals and vector calculus, we can think of the gradient of f as taking the place of the derivative, right? Instead of f prime, we take grad f, which has fx and fy in its components. Let C be a smooth curve given by the vector function r of t, with t going from a to b. Let f be a differentiable function of 2 or 3 variables whose gradient vector is continuous on C. Then the line integral over C of grad f dot dr is equal to f of r of b minus f of r of a. And that right there is the fundamental theorem for line integrals. So we're just coming right out of the gate here and defining that fundamental theorem. So this is all well and good. If we know that we have a gradient vector field, we can evaluate it simply by evaluating it at the endpoints and subtracting. But this does bring up some questions. The first of which is, how do we know whether or not the vector field we're working with is a gradient vector field? So recall from section 1 of this chapter, a vector field is said to be conservative if there exists a potential function little f such that the vector field is equal to the gradient of that potential function. So if a vector field is conservative, then that means it can be written as a gradient. If it can be written as a gradient, then we can apply the fundamental theorem of line integrals to it. Okay, so this theorem tells us we can evaluate the line integral of a conservative vector field simply by knowing the value of f at the endpoints of C. So I got a couple diagrams down here. This property holds in 2D and 3D. So we can see in the 2D graph over here, points A and B, we have the curve C between them. This says as long as the vector field we're working with is a gradient vector field, we can simply evaluate the function f between the terminal and initial points, and that'll give us the value of the line integral. Same thing in 3D with x, y, and z. And notice the interesting part of this, it really, as long as we're evaluating at the endpoints here, it really didn't matter what this curve was. It didn't have to look like this. It could have been something totally different, but the endpoints were the same, and so we should then get the same result. This goes a little bit against what we talked about last time, which was that different paths will produce different values of line integrals. But in order for this to work, they should be producing the same result. So this is the next thing we need to talk about, which is independence of path. So in general, the path we take for a line integral matters, right? The line integral over C1 is not equal to the line integral over C2. But one implication of our first theorem is that given grad f is continuous, the line integral over C1 of grad f equals C2 for grad f. So line integral over C1 equals line integral over C2 as long as we have a gradient vector field. And this is good news because then that means that the curve itself isn't really that important in determining the value of the line integral. What really matters is the vector field and whether or not it is a gradient vector field. In general, if f is a continuous vector field with a domain D, we say that the line integral over C is independent of path if line integral over C1 equals the line integral over C2 for any two paths, C1 and C2 in D, that have the same initial and terminal points. Okay, so if we have a line integral that is independent of path, that means that the path that we take ultimately will not matter. You will get the same result as long as the curves start and end at the same place. So vector fields that can be written as gradient fields are said to be conservative. So we can say that line integrals of conservative vector fields are independent of path. Okay, so if the vector field we're working with is conservative, that means that the line integrals are independent of path. Now, one additional note, we got a lot of terminology in this section, which we'll see on the upcoming pages as well. But one piece of terminology just for right now, a curve is said to be closed if its terminal point coincides with its initial point. So R of B equals R of A. Okay, so if it starts and ends at exactly the same spot, okay, so the terminal point and the initial point are the same. I want to look at this theorem down here, and we're actually going to prove this theorem. You can see I've got a little bit of the framework already set up for us. So we're going to look at this theorem. So the line integral over C of f dot dr is independent of path in D if and only if the line integral over C is equal to 0 for every closed path C in D. Okay, so the line integral would be 0 for every closed path in D. We're only going to prove the forward direction of this. So we're going to say if it's independent of path, then the line integral is 0. Okay, we can also prove that if the line integral is 0, then it's independent of path. But we're just going to prove the forward direction. So we're going to assume that the line integral of f dot dr is independent of path in D, and assume that C is any closed path in D. So a kind of closed path is a path that starts and ends at the same place. So you can see over here on the right, oops, nope, don't want to do that. Over here on the right, I have a closed path. This is completely arbitrary, so this will be our curve C. The way that we're going to approach this is we're going to break this closed curve up. So we're going to choose points A and B, and these are, again, completely arbitrary. So the point A will be somewhere right there, and the point B will be somewhere over here. They don't have to be across from each other. They could be right next to each other. They could be anywhere. Again, it's completely arbitrary. So choose points A and B, and regard C as being composed of the paths C1 from A to B and C2 from B to A. So we're going to say that, let me color code this. So this path from A to B is C1, and this path from B to A is C2. Okay, so we have exactly the same curve, this still closed path, okay, in the domain. We've just attached a couple points onto it and then created two pieces of the curve, C1 and C2. If we do this, then the line integral over C of f dot dr can split up. Okay, so we get the line integral over C1 plus the line integral over C2. Right, so we know that even if the curve is split into smaller pieces, we can still evaluate the line integral over those smaller pieces. Now, we've used the fact that C is a closed path. We have not used the fact that the line integral is independent of path. So I have a little note down here. Note that since C1 and the opposite of C2, so consider the opposite of C2, so that would be the same curve, but going the other direction, right? Same curve, opposite direction, or opposite orientation, if you will. So C1 and the opposite of C2 have the same initial and terminal points, and the line integral is independent of path. That means that they are equal. Okay, so again, follow me on this. C1 and opposite of C2 both start at A, and they both end at B, right? This one starts at A, ends at B. This one starts at A, ends at B. So their line integrals over C1 equals line integral over the opposite of C2. But the line integral over the opposite of C2 is going to be exactly the opposite value of the line integral over C2, right? Opposite orientation, opposite value, right? Opposite direction, opposite value. So what we have here is that the line integral over C1 is equal to the opposite of the line integral over C2. So we can go ahead and sub that in here. So this is opposite of line integral over C2 of f dot dr plus line integral over C2 of f dot dr. This is the same thing, but opposite. They cancel to 0. So if we know that the line integral is independent of path, and we have a closed path in D, the value of the line integral will be 0. All right, let's go ahead and move on to the next page where we have a ton of text and properties, definitions, theorems, all this kind of stuff. So we got a lot of stuff to look at on this next page. And all of this is going to be in service of some theorems we have coming up towards the bottom. So we say that if D is open, then for every point P in that domain, we can draw a disk centered at P that lies entirely in D. So D does not contain its boundary points. So the idea of an open region like this, so like if we don't contain our boundary points, that means no matter where I put a point in here, I can always fit a disk around it, no matter where it is. Even if I go like right up very close to the edge, there's still going to be enough room to fit a disk around that point. Whereas if you have something closed like this, I could put the point right on the edge, and then I can't draw a disk around it because I can't leave the region. Okay, so an open region like this just basically means that there are no boundary points along the edge of the region. If D is a region that we say is connected, then any 2 points in D can be joined by a path that lies in D. Okay. So if D is connected, any 2 points in D can be joined by a path that also lies in D. And we'll visualize this a little bit more in just a minute. Why do we care about open and connected regions? Well, because we're going to start using some of this in our theorem. So suppose F is a vector field that is continuous on an open connected region D. Okay, so we have a vector field. It's continuous on an open connected region D. If the line integral over C is independent of path in D, then F is a conservative vector field on D. That is, there exists a function such that the gradient of little f equals the vector field. Okay, so again, this says as long as we have an open connected region, the line integral being independent of path tells us that the vector field is conservative. Okay. Now, this is all well and good, but one thing that we have not yet been able to do is determine whether or not a vector field is conservative. So we would like to know whether a vector field is conservative or not so we can start using a lot of these properties that it has. So this next theorem says if the vector field F is a conservative vector field where P and Q have continuous first-order partial derivatives on a domain D, then throughout D we have the following relationship. Partial derivative of P with respect to Y equals partial derivative of Q with respect to X. Okay, so again, if the vector field is conservative, then this relationship will be true of its components throughout the domain. Now, this is all well and good, but this doesn't help us show that something is conservative. It helps us show that something is not conservative, because if we show that these two are not equal, that means the vector field must not have been conservative to begin with. But just because these are equal does not guarantee that F is conservative. Okay? Because again, it's if this is true, then this is true. It doesn't necessarily go backwards. Okay? This is not what we would call a biconditional statement. So, and that says, again, right down here, the converse is not usually true. Okay? So the converse, so the opposite of this, if this is equal, then it's conservative, is only true for a special type of region. And we're going to define what that region is right now. So we need a little bit more terminology, and then you can see some gap over here. We're going to draw some diagrams. So first we need to define a simple curve. A simple curve doesn't intersect itself anywhere between its endpoints. So let's look at the different types of curves that we can have. We talked about closed curves back up here on the previous page. And now we're talking about simple curves. So if we have a curve that looks like this, something just nice and straightforward like this curve is simple because it does not intersect itself anywhere between the endpoints. But this curve is not closed. All right, because its starting point and its ending point are different. We can have a curve that looks like this. Something like that. This curve is closed, right? It starts and ends at the same place, wherever you want to begin it and end it. But it's not simple because it intersects itself, right? We could have something like this. This graph intersects itself, so it's not simple, and it doesn't start and end at the same place, so this is not closed. So that's basically the antithesis of what we're looking for. What we're looking for is kind of the most boring curve of the bunch. So it's something much more straightforward looking like this. This curve is simple. It doesn't intersect itself, and it is closed. Okay, because it starts and ends at the same points. Okay. So these are the four kind of general types of curves here. We specifically are going to be focused on simple closed curves. And what do we need those for? Well, to define what we call a simply connected region. A simply connected region in the plane is a connected region D. So remember, if it's connected, any 2 points can be joined by a path that lies in D, such that every simple closed curve, so every curve that looks like this, encloses only points that are in D. So give us a couple examples here. So if we had something like this, so we've got these two pieces here. If these are the region D, so both of these, this region would not be connected, because even though I can draw like a point here and a point here, I can create a path between them. I can't do that between these 2 points, right? I would have to leave the region in order to connect them. So this region is not connected. Okay, so this region is not connected. We could have something that looks like this. This region actually is connected, because I can take any point and connect it to any other point, and I can stay within the boundary of D. Right, this region D here. So this one is connected, but in order for it to be simply connected, every simple closed curve, so something that looks like this, encloses only points that are in D. And like you can do that for, some of them, like this one encloses only points that are in D, and that's great. But I could also just as easily draw one like this, and now it's got all these points in this gap here that are not in D. So that whole means that this is not simply connected. So what are we looking for with a simply connected region? Again, something fairly boring looking, but that's okay. The reason we want the more boring looking ones is because we know nothing unexpected will happen in them. So if this is our region D, every point can be connected by a path that stays in D, and every curve, every simple closed curve in D, contains only points that are also in D. So this would be an example of a simply connected region. Okay, So now the payoff for all of these different definitions comes in the form of this theorem. Let F be a vector field on an open, simply connected region. So an open, simply connected region D. Suppose that P and Q have continuous first-order derivatives, and assume that partial P with respect to Y equals partial Q with respect to X throughout D. Then F is conservative. So this is the reverse direction of that theorem. Okay. And again, notice that it only works on open, simply connected regions. Okay, so regions that look like this and are open, so they don't have a boundary on them. An important thing to note, if you're wondering, like, how will we know that type of region when we see one? Well, the nice thing for us is that a lot of these problems, the domain that we're working over is R2, right? All of R2. R2 has no boundary, right? It continues infinitely in every direction. If you draw any 2 points in R2, you can connect them with a curve that also is in R2. And if you draw a simple closed curve around any section of R2, you will contain points that are still in R2. It has no holes, no gaps in it. So R2 is an open, simply connected region. Which means that as long as we know we're working on R2, okay, so an unrestricted domain on R2, we know that we can use this test. So this is great because now this allows us to just take 2 quick, easy partial derivatives. If they are equal to each other for all values, then the vector field is conservative. And if they are not equal for all values, then it's not conservative. Just like that. Let's try this out with some examples. Determine whether or not this vector field is conservative. So we can go ahead and kind of label these here. So the I component, that's going to be P of xy. The J component, that's Q of xy. So we have, partial P with respect to Y is going to be just -1. Partial Q with respect to X is just 1. And of course, -1 is not equal to 1. So in this case, it didn't even matter what the domain was because the condition already failed. So we can say, thus, F is not conservative. Let's try another one. Determine whether this vector field is conservative. So we're going to have our P of xy, our Q of xy. So partial P with respect to y is going to be 2x. Partial Q with respect to x is going to be 2x minus 0, so just 2x. These are equal for all values of x and y. And again, this is equal for all values of x and y, not just equal for some. Okay, so we can't say that, if we got like 2x and like 4x, something like that, and it's like, oh, well, if I let x be 0, then these things are equal. But it's not that you can find a number that makes them equal, it's that they have to always be equal for every number. So like if I plugged in x equals 1, these two would not be equal. But for this one, I can plug in any values I want, and they will always be equal. So that's the key idea. So these are equal, but that alone is not sufficient. We need to determine if we are working on an open, simply connected region. So we look at the domain. So the domain of f, if we look at any possible restrictions on x and y here, there are none, right? These are both polynomial. So the domain of f is all of R2, which is open, and simply connected. Thus, f is conservative. All right. So we now have a test to determine whether or not a vector field is conservative. And that's great. But if we want to evaluate the fundamental theorem for line integrals, so way back up here, this one, we needed the vector field to be conservative so that we can write it as a gradient vector field. But we also, in order to evaluate this, we need to be able to turn that gradient vector field back into the original function, that potential function, little f. Otherwise, we can't evaluate. So that's the next question. We know how to show that the vector field is conservative. Okay, so this example told us f is conservative, but it did not tell us how to find the potential function little f that is what makes it conservative, right? That we take a gradient of. To accomplish this, we are going to use partial integration. So it's a similar technique to what we saw in our multiple integral chapters. It's the idea of undoing partial differentiation. Okay, so taking an antiderivative with respect to one variable at a time. So let's take a look at the next example. Our first kind of full-fledged example for this section. So if we have this vector field, find a function little f such that the vector field equals grad f, and then we're going to evaluate the line integral of f given this curve C. So note, we just showed that this is conservative. This is the exact same one in the problem we just did. So we know that there will be some function little f. So we know there will be an f such that the vector field is the gradient of little f. If this vector field is the gradient of something, that means that these components must be the partial derivatives of that function little f. Let me say that again. If this is the gradient of something, this must be the fx component, this must be the fy component. So we know fx of xy is 3 plus 2xy, and fy of xy is x squared minus 3y squared. Right? So we know that those are the partial derivatives of the original potential function little f. So what we're going to do is we're going to integrate one of these to get back to the original. I'm going to integrate fx first. You don't have to do fx first, but generally speaking, that's what we do. Integrate fx with respect to x. So we take the antiderivative of this with respect to x. So that's going to be 3x plus, that'll be x squared, and the y will just tag along. Okay. Again, if you don't believe me, take the partial derivative of this, and you'll see you get back to here. But we know with integration, we would normally have to add that plus c, right, that constant of integration. But it's not quite the same with partial integration because there could be a constant that got added on here, but y is being treated as a constant. So there could also be some y's here that when we took the derivative, they disappeared also. So instead of a plus c, we're going to add a function, g of y. Okay, and we're going to add this because this is constant with respect to x. So it's just like adding the plus c, but because there could potentially be y values that are treated as constants, we have to include them as well. Okay, and there may be nothing there. We don't know that, but we have to be careful just in case there is something there. All right, so this is our kind of rough draft of the function f, right? That's what we're looking for, the function f. We know most of it. We just don't know if there's something here where this g of y is. So what we're going to do is we're going to differentiate with respect to y. So we're going to differentiate the function we just got. That's going to be 0. This is just going to be x squared plus g prime of y. And we can put g prime, so I know this is kind of a blast from the past. We haven't used prime notation in a while, but we can use g prime here because this function only potentially has y's in it. There will be no x's in this. So we can just use g prime of y. Now we're going to compare. So compare what we just got with what we know fy is. So we know that fy is x squared minus 3y squared, right? We established that at the beginning. We just found fy is x squared plus g prime of y. So comparing directly, x squared checks out. G prime of y must be equal to this, to negative 3y squared. So g prime of y must be equal to negative 3y squared, which means that g of y will be negative y cubed. Right? If we take its antiderivative, and we do need to add the constant here because there could still be a constant we don't know about. Instead of using c, we don't really use c as much in these types of problems because c is already kind of set aside for the curves. So we'll use k a lot for the constant. Right? So that was the missing piece. So thus, f of xy is, so we're back to the blue one right here, 3x plus x squared y minus y cubed plus a constant k. And that would be the potential function. That is the function whose gradient is that vector field back up there. Okay, so we showed that the vector field was conservative. That means it is the gradient of something. This is that something that it is the gradient of. Now, using this information, we can apply the fundamental theorem for line integrals to solve this line integral over this curve from 0 to pi. So for part B here, so use the fundamental theorem of line integrals, or I guess that's fine, FTLI, fundamental theorem for line integrals. We can just abbreviate it that way. All we need are the initial and terminal points of C, since our vector field is conservative. So we start at 0, we end at pi. So we need to plug into R at those endpoints. So we're going to have R of 0 is going to be e to the 0 sine of 0 I plus e to the 0 cosine of 0 j. That's 0 and 1. So that's the vector 0, 1. R of pi, that's e to the pi sine of pi, I, plus e to the pi cosine of pi, j. Sine of pi is still 0. Cosine of pi is negative 1. So we end up with 0 and negative e to the pi. Now, when it comes to evaluating for f here, we can just take note that when we evaluate this between these two endpoints here, we will get this function plugged in here minus the function plugged in here. You're going to get a k minus a k. So it really doesn't matter what value k is because it's going to subtract itself off anyways. So any value of k will disappear via subtraction. So we can let k be equal to 0. Okay, so when we're evaluating using the fundamental theorem, we don't need to actually show k in that formula because we know that it's just going to get canceled out anyways. So we have line integral over c of f dot dr is the line integral over c of the gradient vector dot dr. That's f of 0 comma negative e to the pi minus f of 0, 1. So we plug back in to here. So that's x is 0. So that's 0 plus 0 minus negative e to the pi cubed minus 0 plus 0 minus 1. So we get, that becomes a positive, so that would be like e to the 3 pi, and then plus 1. So that would be the value of the line integral, found simply by using the endpoints of the curve rather than the entire curve itself, because the entire curve itself didn't really matter. All that mattered was where it started and where it ended. because the vector field is conservative, so it's independent of path, and that allows us to use the fundamental theorem for line integrals. Now, all of this does extend up into functions of three variables. So if we look at the next page, so we can still apply all of the same principles to these functions of three variables, and the process is going to be the same. We just have to do it another time. Basically, we have to kind of repeat our steps a little bit. So this vector field, we can assume that it's conservative for right now. We'll show later on like how we show that a 3-component vector is conservative. But let's go ahead and find that potential function. So we have fx of xyz will be y squared. Fy of xyz will be 2xy plus e to the 3z, and fz of xyz will be 3y e to the 3z. So if we look at the steps that we did in the previous problem, we integrated fx, differentiated with respect to y, and compared against fy to find the missing piece. We're going to do the same thing here, just a couple of times. So we're going to integrate fx. So we're going to get f of xyz equals xy squared plus an unknown constant, but that unknown constant can contain y's because it's treated like a constant, and it can contain z's. So we're going to have g of yz here. Then we're going to differentiate with respect to y. So we get fy of xyz. That's going to be 2xy plus the derivative of g with respect to y. Now we can't use the prime notation here because there are two variables. So we get gy of yz right there. Compare against fy. So we already had fy up here. So now we're going to compare this one to it. The 2xy checks out, and we have this piece left over. So gy of yz must be e to the 3z. So if we take the antiderivative, so g, the original g, must be y e to the 3z, right? Because z is a constant, so we just pick up a y here. Plus, not just a constant this time, because there could still be a function of z. So we add h of z into that. So now checking in with our original, we have xy squared plus, so we have xy squared plus g. Xy squared plus g is that. So plus y e to the 3z plus our unknown function of z. So now we still have one missing piece, but we still have one partial derivative we haven't worked with yet. So we're going to go ahead and now differentiate with respect to z. Okay, so now's the time when we start repeating ourselves. So we get fz. First component becomes nothing. Second one, we get 3y e to the 3z plus h prime of z. And now we go ahead and compare fz back up here to fz down here. 3y e to the 3z plus h prime of z plus nothing back up here. So what does that mean? Well, that means h prime of z is nothing, which means that the original h of z must have just been a constant, k. All right, that's the only thing it could be, because this is a function of one variable now. So now we have the last missing piece that we needed to that original function. So we can say, thus, f of xyz equals xy squared plus y e to the 3z plus k. And that is our potential function. And then, of course, again, if you're not sure if you did it completely right or you just don't believe, you can take the gradient of this. So, like, to check it, find grad f and show that it's equal to the original vector field that we had back up here at the top. So find the gradient and show that it's equal to the original vector field. That would be the way we could check our work and make sure that we found the proper potential function. All right, so that brings us to the end of section 16.3. When we come back in the next section, we're going to be still evaluating line integrals, but we're going to look at some new theorems and properties that allow us to evaluate them in new and different ways. So I will talk to you all in that next section.